Go. I have the problem. I'm going to try and take the antiderivative. And so when I see x to the negative 3, well, that becomes x to the negative 2, because I add 1 to the exponent. But then I have to put something out front. So what am I going to put out front? And then here I have minus 8. I'm going to make that minus 8x. Okay? And then since it's a definite integral, I don't need a plus c because I would just end up subtracting it. So instead I'm going to write over here the limits of integration. The lower limit is 1/2 and the upper limit is 1. And now I'm going to substitute in. So I'll do my f of b minus f of a now. So when I substitute in 1, I get negative 1/2 times 1 to the negative 2 minus 8 times 1. And now I will subtract what I get when I plug in 1/2. So let's see, that's negative 1/2 times 1/2 to the negative 2 minus 8 times 1/2. And now it's just a matter of, can I simplify things correctly? Okay. That's what I get so far. So let's see. Here I get, well, 1 to anything is just 1. So this is negative 1/2 minus 8. And then I had a couple of negatives here, but I'm subtracting it, so it's going to become positive. So I get plus, well, this is 1/2, and this I can think of as 2 squared, right? If it's 1/2 to the negative exponent, I can make it a positive exponent and just take the reciprocal. And then this is 4, of course. But it's going to become plus 4, because again, minus, minus. All right, so let's see what we have. Here's half of 4. That's 2 plus 4 is 6. Minus 8 is negative 2. So I'm getting negative 2.5. Is that what they had, Chris? Or? Okay. Do you guys have questions on that? Okay, so that's 37. And then, Joe, you asked about 65. So let's look at 65. Going here. I got to go down a little bit. Yeah, we didn't do one exactly like this yet, okay? So this is, we just demonstrated part 2 of the fundamental theorem. Clearly this one wants me to use part 1 of the fundamental theorem, right? And so I have the derivative from negative x to x of the square root of 1 plus t squared dt. Hey, by the way, you know, when we did these derivative problems, some of them you can do. I think the first time I did one for you, I did number 59 in class. You remember that yesterday? Or Monday? And I did it the long way first. And then the short way. The short way, what's the answer to 59? What's the derivative of that integral function, that area function?
X squared plus x plus 1.
Yeah, it's x squared plus x plus 1. That's what the fundamental theorem tells me. First I did it the long way. I did the antiderivative, got something, plugged in the x and the 3, and then I took the derivative. Okay? Now the funny thing about this one, number 65, is if I asked you, hey, do it the long way, you'd be out of luck. Because we don't know how to find an antiderivative. Well, I don't think. You guys know how to find something whose derivative will give you the square root of 1 plus t squared. Today, we're going to learn a nice technique for finding lots of antiderivatives we haven't been able to find. Unfortunately, that's not one of them. You won't be able to do that till the middle of Calc 2. All right? Just leave it at that. And there are even integrals that nobody can do, that I can write down right now. And I'll show you that today also. Okay? So kind of makes you step back a second. Well, I'm learning all this stuff, but there's some problems that I just can't integrate. Okay? This is one of them. Yet. I'm going to show you how to in Calc 2 if you guys stick around for a semester. Okay? We have to do it the short way, but the problem is, okay, let me go to what I'm working on. The fundamental theorem works if you have a lower limit of a, some constant, and an upper limit of x, which is which is my variable. So, I guess what I would recommend is this. I'm going to start this problem by saying this is equivalent to the derivative of, and I'm going to write it as a sum of two integrals. So I'll pick some point A in between negative x and positive x. Maybe I'll pick 0. That's in between negative x and positive x. So let's say that this equals, you guys saw this trick once yesterday. I think we did it for the problem Stephanie asked about, if I'm right, on Monday I should say. And so I'm going to split it up into two area functions, well, two integrals. You've seen me do that one other time. Does it make sense to you? Let me see if I can show you a picture that'll help it make sense. What I did was this. Let's see what the graph of the square root of 1 plus t squared looks like. Real quick in a calculator. So I want, clear this out, and I will just graph the square root of 1 plus x squared. And let me graph it. Okay, there it is, right? Now, how's this work? Well, remember, it says we want to we're talking about an area function, but it goes from negative x to x. So, like, you could put in, you can integrate on this calculator, and it'll do either like something like left sum or right sum. So if I go from negative 1 to positive 1, it'll compute that area for me, right? And then I could say, no, I'm going to go higher. I'm going to do it again. I'm going to integrate from negative 2 to positive 2. It didn't work. Why not? That's weird. Try that again. Integrate from negative 2 to positive 2. There it is. Now it gives me more area, 5.9. You guys with me? So this is a different area function. It's not starting at A anymore. It's kind of expanding in both directions. And I'm trying to compute the derivative of the area function. Well, okay. So I said let's write it this way. And then I think what you want to do, see this one, I know what the derivative is, right? We're going to take the derivative of this in pieces. Because I know when I have a sum, I can take the derivative in pieces. So what's the derivative of this one going to be? Well, square root of 1 plus x squared, right? That's no problem. Now what about the first one? Well, there's another trick I've done one time in this class, and here comes time number 2. I will say that this equals the derivative of, so I know what this one's going to be, but I'll say that this first piece equals the derivative of negative integral 0 to negative x square root of 1 plus t squared dt. Why? Well, if you're switching these, what letters do we usually use for these two limits of integration? We usually call these things A and B. So I just switched them, And so now the fundamental theorem tells me instead of doing f of b minus f of a, I'm doing f of a minus f of b. How are those related? Well, one's the negative of the other. You guys with me so far? Yeah, kind of. Do you have questions so far? So I've made two moves here that I am very comfortable with and are very new to you. This is only the second time you've seen either of them. One of them was to split this up into two integrals. And the second was I can change the order of integration. Now I'm almost there. Now you have to think about one more thing I did last class, and that's this. Do you remember what we said would happen when you took the derivative and there was something besides x up here? Which rule did I have to employ? I did a substitution, yeah, because then I wanted to do the chain rule, right? So, what I'll do is I'll say here, let u equal negative x. Okay. Then what's du dx? Negative 1. Okay. And if I call this big mess, the whole thing, if I call this big thing a of x, then I can say that a prime of x is equal to a prime of u times du dx, okay? And so in other words, I'll take the derivative of this, but I'll have to multiply by negative 1. Negative 1. Okay? So when it all works out, let's see what I get. Take the derivative of this, the a prime of u. What I get is negative. What's the derivative of this red thing? Well, remember, it's square root of 1 plus x squared times negative 1 because of the du dx. Plus the other one I had. So final answer? I'm getting this. Is that what they had in the back? Okay. It's 2 times the square root of 1 plus x squared. Here, let me give you one other reason that this is the answer. Okay? Go back here. The integral from 0 to x is this thing, right? So let me give you another approach. The derivative of this integral is equal to the derivative of twice 0 to x 1 plus t squared dt. And I'm going to say this is true by the symmetry of f of t equals the square root of 1 plus t squared. That when you look at the graphing calculator and you say, hey, this is a graph of square root of 1 plus t squared, it's symmetric along the y-axis. Actually, what kind of function is that? Remember what kind of function that is if it's symmetric along the y-axis? That's called an even function. If you have an even function, there's a really nice trick you can do. Instead of integrating from negative x to x, here, let me do an example one more time. I will do an integration from negative 1 to positive 1. It says my answer is 2.295. Another way to do that would be instead, so that's about 2.3. Instead, you can integrate just from 0 to 1, and then double the answer. So let me try that. I'll integrate from 0 to 1. That gives me 1.15. Double the answer, you have your 2.3. It doesn't show it, but it only found this piece that time. The problem is it doesn't erase. So I'd have to erase to kind of show that a little bit better. There's the original, and then go from there. The reason I split them is because for the fundamental theorem part 1 to work, okay, what does the fundamental theorem say? It says that you know how to find the derivative of an area function that looks like this, a to x f of t dt. It says that this will be f of x. But it only works if I have a constant down here. And I looked and I said, oh, I don't have a constant, I have a variable. So I'll split it up. Then this one will have a constant. And I'll do my flip, and then the other one will have a constant. And then I did chain rule because the other thing you need is you really want to have just an x here.
Right.
So there's a lot going on in order to be able to use that theorem.
But in the book, sometimes they split them for other, to do
Yes,
too.
yes. They do split them for other reasons. The question you asked last time was about the picture. And I remember it was something like, I don't remember, but it was something like this, there was a cusp. And we realized that if we integrate from here to here, and then integrate from there to there, it works out better. Yes, this is a trick that will not go away. You're going to be splitting integrals for a long time here. Okay? Actually, section 4 talks a lot about when to split integrals. However, section 5 is harder and more important. So I'm doing it first. We'll come back to your question on Friday. Okay? You guys ready? Go ahead, Mike.
So can we say from the anytime we have...
That's a good question. When would I ever do this? I mean, most functions you can think of, are they even functions? I don't know. I guess not, right? And yet there's a lot that are. Can I have an example of an even function? Y equals x squared.
Almost any normal parabola is that.
The parabolas, as long as you think of 0 in the right place, then yeah. How about a trig function? Which trig function do we know that's even? Cosine is even, because it goes through 0, 1, and then it kind of, right? And the other thing is, I'm talking to a bunch of future engineers here. Now, we're talking about finding area under curves, but let's up it a dimension and get ourselves in Calc 3. Now we're finding volume under surfaces. And a lot of surfaces have symmetry. You make a jet engine. You want to know its volume. Well, if you put the axis in the right place, you have all kinds of symmetry, and when you integrate, good things happen. So this is a technique that's not going to go away. There's a reason I'm showing it to you. So I'm glad you asked that, though. That was a good question.